Mr. Tran.
Yes.
Oh, you remember from last semester, you're my advisor when I was picking my classes. So I want to ask you some questions. If you're not busy,
Well, I'm about to teach soon. Is it quick?
you just quick.
Sure.
So I was registered for my classes. So those 500 level courses, you need a permit. So how would I be able to get that permit? It says like approved, like graduate plan. So I would have to book a appointment with an advisor.
No, so you'd have to get permission from the instructor. So once the instructor is posted, you would contact them directly, so you can get their email address straight from the class schedule. Usually they're going to want to see your transcript just to make sure that you've taken all the prerequisite courses and then make sure you're doing well in them. And then once if they give you permission, then the department can issue a permit in that case.
Okay, and if I take the class, could it count as credits if I wanted, let's say,
Usually we count it as a technical elective. Yeah.
you can't count it as a graduate level course, like that you could
Well,
units in graduate school?
So the first thing you have to satisfy are the technical electives. And so if you satisfy, so let's say you take 4 technical electives and then you take a 500 level course, then you can count that 500 level course as a graduate course from there.
A 4 level courses don't.
You can, but if it's extra. So you have to take 4 technical electives first. That satisfies your undergraduate requirements. And then anything you take on top of that, a technical elective or 500 level course, then you can count those for grad credit. You can't double count. That's the main thing. So if you use a course to count for your undergraduate, you can't double count it for your grad degree.
Okay, so I can start my graduate unit courses once I have my 4 technical electives complete.
Correct. Yeah.
And those can be anything. Those can be even 400 level courses.
As long as they're technical electives. So
Yeah,
a technical elective is a 400 level course that's not required.
Mhm.
Yeah. So any 400 level course that's not a required course, you can count as an elective.
Okay, so there's no like special like, so from what I heard, that when you take those classes, let's say like a 4 level course, you have to ask for a special exam to make it count as very level. So is that something that's the thing?
Right. So if you're going to take, like, let's say you take your 5th technical elective and you want to count it for graduate credit, then you have to do an extra assignment in the class. That's typically how it is to count it for grad credit.
And I would have, so those 4 courses that I take, those wouldn't count as graduate level courses.
No.
It's like, what if I took like total of 8? And because I don't know if it matters if you count specific ones and don't count specific ones.
Well, it's whatever the last 4 that you take.
Okay.
So the first 4 you take, no matter what, those will count towards your undergraduate, and then anything after that you'll count towards your grad degree. You can only take a maximum of 3 as an undergrad. So you can take a maximum of 7 technical electives. After that, then we tell you to wait until your master's degree after that.
Okay, right. Thank you.
Yep. All right, it's 4 o'clock. Let's go and get started. All right. So welcome everybody. There's literally zero people in the classroom except for me. This feels like COVID again. How's everyone doing today? All right. Good, good. Glad you guys doing well. Okay. So plan for today, I just have kind of half a lecture today. This is the last time I'll be speaking, for the class. Today our lecture notes are on flow phantoms. So a little bit of experimental hemodynamics today. So we've spent the entire semester talking about computational computational methods, computational techniques, all the math, the simulations, things like that. But there's a whole field, there's a whole branch of kind of experimental fluid mechanics that we didn't cover. Mostly just because I personally don't have a lot of experience in that field, but it's still very interesting and very important for the work that we do. Because the thing is, as powerful as our computers get, as powerful as our simulations get, at the end of the day, we still live in the real world. In order to validate, in order to test a lot of the things that we discover in simulations, there always has to be some kind of experimental component to it. There's just kind of no way around it. No one is going to perform surgery on a person based purely on just simulations. You have to have some real life testing done before that can be done. So that's what we're going to talk about today. So I think these lecture notes are probably only going to take, I don't know, maybe like 30-40 minutes. And then just like on Tuesday, for the rest of the time, we'll have project workshops. So if you have questions on your project, you have questions on the meshing, the boundary conditions, anything like that, that would be the perfect time to ask. And then the plan for next week. So next week, I don't have any lectures planned. Next week are just going to be open office hours. I was telling this to my grad students too, that over the next couple of weeks, I expect my office hours to be pretty busy for the most part. Today not so much, but over the next couple of weeks, basically all my classes, all three of the classes that I'm teaching are working on final projects. So there probably will be a line, waiting for feedback and office hours, especially during finals week. So I would definitely take advantage of the lecture times that we have next week to get your questions answered about your projects. Because at least during the lecture times, I'm going to be dedicated to just 442. So I would definitely get a head start on your guys' projects until then, just so that you kind of take advantage of the class time that we'll have. Okay. All right. So yeah, so that's just the plan. Pretty straightforward, pretty chill today. Any questions I can answer before we get started? Before you guys came in, I took a picture of a completely empty classroom. So yeah, I was saying that today, I just have kind of like half a lecture planned for today. Oh, there's people on Zoom. There's people on Zoom. Yeah.
Professor,
What's up?
I just want to clarify. So next week, along with the normal office hours, class time will be considered office hours too.
Exactly. Right. Yeah.
Okay.
Yeah.
All right. Thank you.
Yeah, because we're moving into final production. I think most people are getting started on the final projects now. So I would definitely start it over the weekend so that you can come to lectures next week and get your questions answered. Yeah.
Okay. Thank you.
Yep. Okay. All right. So today we're talking about flow phantoms. Really kind of interesting work, and I wish I kind of wish I had gotten into this a bit when I was doing more research full time, but because it's cool and it's something that you don't really see every day. Okay, so let's talk about what flow phantoms actually are. So it's a cool name. It doesn't really have anything to do with ghosts or anything like that, but we use the term flow phantom to talk about these kind of like almost like real life kind of recreations of the cardiovascular system. So here we have a couple flow phantoms here of the aorta and the heart. And it's actually really interesting to see them like this too, because I think for the most part, all of you guys have been looking at aortas and blood vessels and some vascular makes things actually look much bigger than they actually are. But remember, these are blood vessels that kind of fit inside your heart or fit inside your body, excuse me. And the vessels themselves, even the biggest one, like the aorta you can see right here, only has a diameter of 2 to 3 centimeters. And so when you put it in a box like this with all these kind of flow tubes coming out of it, it really kind of highlights to you how small these things actually are compared to when we see in a computer. Everything in a computer is kind of blown up to whatever size of the monitor is. So, it's kind of cool to see it like this. But, like I mentioned that, as sophisticated or as complicated as our computational methods are, and honestly, our computational methods have come a really long way over the last few years. End of the day, we still live in the real world, right? We don't live in a simulation, or at least not that we're aware of, right? And so, any kind of a real life, real kind of experimental testing setup where you get real life data, that's always going to be important, right? And I say this as someone who I kind of identify as someone who's strictly a computational engineer. That sometimes there can be a little bit of competition between the computational folks and the experimental folks of who's better or whatnot. But even as a computational guy, I know I'm grounded enough in the fact that there's a lot of the work that I do is meaningless unless there's kind of a real life component to it. So you can do experiments to verify what we're doing and to test things out before you put them into a real person. So this is kind of its own field in itself, and the reason it's kind of its own field is that for cardiovascular applications, the geometries and the fluid mechanics and the properties and the kind of the biomechanics are all extremely complicated. And so if you want to recreate a lot of these, even just the geometry in a lab, it's a very involved process, and it takes a lot of expertise in experimental fluid mechanics to get to work. And so the term that we use for these kind of setups here are called flow phantoms, because they're meant to phantom or meant to mimic the flow that goes into these setups. Okay. So what we're going to talk about today mostly is about the construction of the geometry, so kind of the processes that you have to go through to construct something like this. But just know that there's kind of a big, this is a whole big kind of field in its own. They have their own conferences, and they don't even invite the computational people because they think they're weird. Okay, so why would we want to use these flow phantoms? So let's go into a bit more detail in terms of why you would want to do this. Okay, so when you're talking about the cardiovascular system, these are kind of living, breathing systems, right? So most time when you scan someone, that's a living, breathing person. So on the one hand, people say that you can get what's called in vivo measurements. And so in vivo measurements refer to measurements within a person that's actually living. So that usually involves sticking a probe into someone or maybe measuring with an MRI machine, something like that, right? So these experimental setups, these flow phantoms, are different than in vivo. Okay, so in vivo actually means taking a real person and measuring the flow inside of them. So, but there's a lot of advantages to using a flow phantom rather than just measuring inside the person. So the number one reason is control, right? So if you've ever run experiments before, you know that there's so many different factors in the real world that you have to kind of account for. And any good experimentalist or any good kind of well-designed experiment will do its best to kind of control every single factor of the experiment, except for the thing that you're trying to study, right? And so the thing is with in vivo measurements is that, you have very little control over the person's condition. First of all, you have very little control over what their anatomy exactly looks like. But you have also very little control over how they're feeling in the moment. So like if they're starting to feel stressed, if their heart rate starts to go up, if their hormones start to kick in, you have no control over that. But if you have an experimental setup and you instead control the flow with a mechanical pump, with a pump controller, you have direct control over the flow and the pressure and the pulsatility and the heart rate of everything that goes into your experiment, right? So that's the number one thing, right? And that kind of a difference there is kind of what most experimentalists will say is true too, right? There's a difference between observing something in the wild, like observing birds' behavior, rather than putting the bird inside a lab where you can kind of exactly control everything. All right, number two is very closely related to number one, is that if you run an experiment in your lab where you can kind of carefully control all the factors, it's going to be a lot easier for you to reproduce your results, right? And reproducibility is a very important part of just experimental physics or experimental science in general. And so, if you want to prove something, if you want to, make a truth about the world, you have to show that it can be repeated. You have to show that it's consistent. And doing something in a lab is a lot easier to kind of do that for you. The number three reason to use flow phantoms has to do with licensing and safety. And so, because cardiovascular, we work kind of with real people. In order to measure someone, you have to, cut someone up or stick something inside of someone, which involves kind of waivers, involves kind of liability, things like that. So if you do something in a lab, there's no danger to anyone. except maybe the mental health of whoever's running the experiment. But no one is put in any physical danger by using a flow phantom. Okay. And the number 4 reason, probably the coolest reason, is just optical transparency. So, what you can see, from this previous image here, that most of these flow phantoms are made of transparent materials so that you can actually visually kind of see the flow going on. That's not true for humans, right? So, we have yet to invent X-ray vision. And so it's impossible to kind of directly visualize the flow inside a person the way that you can with the flow phantom. And so that optical transparency is actually really key. So you can use a lot of high-speed cameras, you can use a lot of measuring equipment to measure flow with a degree of accuracy that you would never be able to achieve in a real person. Okay. The main disadvantage of using a flow phantom is that they can be very tricky to manufacture. It's a little bit easier now with 3D printing. So 3D printing has gotten a lot better to make these a bit better, but it still can be pretty challenging. So that's definitely one thing to keep. Okay, so what are flow phantoms used for? So there are 3 main uses for flow phantoms. And so the number 1 reason is to, first of all, just investigate the flow field. And so if you want to visualize how the blood flow looks like in certain kinds of geometries, you can very easily do that with the flow phantom. And you can even, in fact, use a lot of optical imaging systems. So very high-speed cameras, very powerful cameras. You can use techniques like particle image velocimetry, which we'll go over in a second, where you can actually kind of visualize the flow using a laser. That's super cool. Okay. Number 2 reason to use a flow phantom. This is what I'm most accustomed with, or a lot of this is what I work with a lot of my collaborators for, is to validate your simulations. So we didn't really talk much about this in this class. Maybe for those of you who are in the CFD class, you may have talked about it a bit. But a simulation by itself is actually kind of useless. And so in order for you to use a simulation for anything practical, you have to show that it's actually a representation of real life. And believe it or not, that's not a given. And so it's very easy to set up a simulation in a way to give you basically garbage results, right? There's a saying that we use in the computational world, which is called garbage in, garbage out. And so if you don't set up your simulation properly, if you don't set up your boundary conditions properly, or your mesh is not very good, you're going to get pretty bad results. And so being able to validate your method, being able to show and prove that, the way that you're doing things, the way that you're setting up the boundary condition, the way that you're meshing, that it actually does match up to reality is really important. And that's an important step for people to actually use your simulation results accurately. So every good computational person is very good friends with an experimentalist, just because we need the experimentalist to kind of show what we're doing is actually legit. Okay. There's actually another saying that that's used in computational world, is that if you do simulations for a living, if you do computations, kind of the saying is that nobody will believe your results except for you. Because everyone, it's very easy to kind of question what you do in a simulation, whether you set things up properly or not. And so if you ever present your work, or if you ever kind of show off your simulations in a report, people are going to criticize your work much because there's so many different ways to go wrong. Whereas if you do experimental work, the saying is opposite. So if you do experimental work, everyone will believe your results except for you, because people tend to trust experimental results a lot better. But only maybe you took some shortcuts, or maybe things didn't set up correctly, so that might have polluted your results. So that's kind of the paradox that you work with as computations. And the number 3 reason to use a flow phantom is to investigate the relationship between flow and biological function. And so there's a new class of flow phantoms that are being developed nowadays that actually implant endothelial cells within the flow phantom itself. So this right here, this is not a good example. This is probably just made of acrylic. So I don't think there's any kind of living cells here, but it's actually starting to become possible to 3D print some materials where you can implant some living cells, and you can actually put flow onto the phantom and actually see how the cells react. And that's unprecedented, because otherwise you'd have to kind of cut open a person to see that. And if you cut open a person, you're probably going to kill the cells at the same time. So the ability to kind of observe cells in their kind of natural environment and have them survive and have them react is actually really important. And that's actually become a very big emerging field right now, as we study things like mechanotransduction and cellular response and things like that. Okay. And so there's a wide variety of different applications that flow phantoms can be used for, and what you end up using the flow phantom for is going to determine how you construct it. And so typically, and this is not unique to flow phantoms. This is true for most experiments. Most of the time, you formulate your research question first, and then based on your research question, based on what you're trying to find, then you build your flow phantom to try to answer that question, or to get the data that you need to answer that question. Okay. All right. Any questions on this so far? Okay. All right. So let's talk about flow visualization, because I think this is kind of the coolest thing that that flow phantoms can do. Okay. So because most flow phantoms are made of this kind of transparent material, you can actually very detailed, in a very detailed way, visualize the flow that's going through. Okay. So this is accomplished by using an optically transparent material, so something like acrylic or something like that. Okay. And then they use cameras or other kind of measurement devices to view the flow. Okay. Another thing that's common is that the fluid is often seeded, and so there is either particles or some material or some kind of dye that's used within the flow to make it easier to kind of pick up on cameras, right? So this right here is actually a very beautiful image, because what this experimentalist did was they used a bunch of particles, very tiny particles that are luminescent, and so they kind of light up when you shine a laser onto it, and so you can actually kind of very clearly kind of see the streamlines of the flow as they kind of flow past this this bulge right here. So something like this, we take it, I think, for the most part, we take it for granted, because something like this you can kind of very easily produce in a simulation or something like that. But to get actual kind of measured, kind of captured flow like this with the camera in real life is actually very significant. So this right here is a particularly beautiful image for that. Okay. The tricky thing is that if you are going to use particles, or you are going to use something that, in order for it to not affect the flow, they have to be buoyantly neutral. And so what that means is that they have to be made of material that has a very similar density as the flowing fluid. So you don't want to use a particle that's too heavy. So if you use like a metallic particle, all of those will just naturally kind of fall to the bottom, right? Or if you use a particle that's too light, there's going to be a buoyant force that kind of pushes it upwards as well. So you want to minimize that buoyancy effect. So you want to make sure that it's as neutral as possible. So when you see the flow with particles, then they'll just kind of stay suspended there and won't move unless you put flow onto it. Okay. And so with that, let's talk about particle image velocimetry, or PIV. So this is probably the most common way that people use flow phantoms to visualize flow. And so under this method right here, the flow is seeded with all these little tiny particles. And then basically a laser sheet is shined through the flow to visualize that flow within a single plane. Okay? So this image right here was actually imaged with particle image velocimetry. Okay? So the way it actually looks like, so before you input any flow, so you can see here that the flow here is completely still. So we have a bunch of these particles that are just suspended. And as soon as the pump is turned on, or as soon as the flow is driven, these particles will all start to move. Okay? And then as you capture the images with the laser sheet, then you'll actually see the path lines kind of go through. So I have a video that kind of shows you how it works. We won't see the whole thing, but PIV is actually used very commonly in the aerospace field as well, because oftentimes, so let's say that you were designing an airfoil and you want to visualize the airflow that goes over the airfoil, so that you can see whether there's any kind of points of separation, any vortices that occurs. You would use PIV to kind of visualize that. Okay, so I have this video here. So we'll actually, I think I need to share my screen with sound. Let me do that quick. Okay, so we'll play this video for a little bit. This guy actually he looks very similar to one of my old colleagues, but he's not. But you can kind of see how.
Okay, so today I'm going to show you how we experimentally.
Oops, sorry about that. I was trying to maximize it and I pushed forward.
Okay, so today I'm going to show you how we experimentally visualize airflows and get numbers on airflows. And the way that I normally do that is through a technique known as particle image velocimetry, or PIV. It's a fundamentally simple technique at heart, but it's quite complex in reality. So I'm going to show you through some of the basics and talk you through the experimental facility here. So
Basics of PIV. To start with, you have a wind tunnel. I've lopped off the front of the wind tunnel in this diagram for clarity, and just indicated where the flow is coming into the tunnel with the flow arrow. The center bit is the test section, which is where you put the stuff in that you want to look at, and then the back is the sort of exit diffuser or expansion that goes into the tunnel fan. It's this relatively small bit, the test section, that's what we're interested in. Now, because I've got a long diffuser expansion section on my tunnel, I've actually put a camera in that section there. Now, why I've got a camera here will become clear later. Up the top, there comes a laser sheet down that's held by a laser probe that's on a traverse. The traverse allows the sheet to move forwards and backwards. This allows me to look at different sections of the airflow as it goes along. For a more three-dimensional representation of this setup, we can see here the laser attached to the traverse holder at the top and the camera shooting at the back. Now, the point where the camera looks at where the laser is illuminating is the bit that we're actually looking at and trying to investigate. But why do we want random images of a laser sheet? Well, simply put, we seed the room with a lot of particles, kind of, you can imagine, like a sort of smoke, but it fills the whole room and is quite a consistent density. And this laser is actually fired in pairs. So we get multiple pairs of images at really close spacing. We're talking sort of 50 microseconds or less, so very, very tiny time spacings. So when we get these two images here, we get them received at the camera, and between the two images, the flow has moved somewhat in the tunnel. So we look at those two images, we see what the difference is between the two, and from that we can see how much the flow has changed. Now, we can see stuff actually because we have images of the particles, and we can see the particles because the laser at very high intensity is shooting those particles, and the light is scattering off those particles and being reflected back to the camera. So for this testing today, we've got two veins, the laser probe, and that's what we're going to be looking at, just two vortices of two veins.
Two wings will make vortices.
Yeah, so that's the basics. So then from there, he kind of just describes his own experiment, which is his research in aerospace. But basically, you shine the laser at a couple points in time, and then you see kind of how the particles move. It's very, if your laser sheet is fast enough, the particles don't move that much from one point to the next. And then from there, you can see the direction of flow and the velocity, and you can compute things and kind of visualize in a very, very nice way. So that technique, PIV, was actually developed, primarily for aerospace. But then, it's since been applied to a lot of other places as well. That's kind of the common theme actually too. So actually, a lot of what we talked about in this class, a lot of these techniques were actually developed for aerospace engineering first, and then we've since applied those techniques to biomedical fields. So a lot of what we learned in this class kind of owes a lot of it to aerospace engineering. Because if you do any kind of fluid mechanics, aerospace engineering is kind of the forefront of doing that. Okay, so let's talk about how to construct these flow phantoms. And so, like I mentioned, typically these flow phantoms are constructed of some kind of optically transparent material. But the most difficult thing is the geometry. Okay, so the most common materials for the phantom construction are glass, acrylic, polyester, or silicon. All of these can be made optically transparent. Okay, and because of the complex geometry, usually some kind of casting method is used to construct these flow phantoms. 3D printing is becoming more popular, but I think with 3D printing, there's some limitations to that as well, because you want this internal surface to be kind of as smooth as possible. And typically, a lot of 3D printing, you kind of build it up in layers. Sometimes it's really hard to kind of not get some of these kind of layers to kind of be within your flow phantom, but it's getting there. 3D printing is definitely improving. Okay, so here's kind of one sample process. This is kind of an old school process to kind of develop one of these flow phantoms. So the first thing that you start with is a CAD model for your blood vessels. So let's say that you construct a model like this in Simvascular. So you take a person's image data and you make the path and the segmentations and you make a model like this. Okay. Then from this model, then a mold is created. So a mold to kind of basically form from this shape. Maybe this is 3D printed or not. Okay. It is 3D printing. Typically, it is 3D printed. Okay. Then from there, some kind of low melting point metal is poured into a mold to form a core. So that's kind of what you see here, right? So basically, a cast is formed in step 2, and then step 3, some kind of low melting point metal is kind of poured in to kind of make the shape like this. And then once you kind of have this internal shape right here, you can kind of sand it down because, you know, from the 3D printing, you may have some kind of surface roughness that occurs due to the layers. But once you kind of make it from metal right here, you can sand it down pretty easily. Right? Okay, then this low melting point metal is then poured into a container with inlets and outlets. So oftentimes you want to design these so that you can actually put flow into it. So you can see here that from this image right here, we have these kind of inlets that kind of screw onto some pipes that may come off on the back end. Okay. And then some kind of silicon or some kind of acrylic polymer is then poured on top around the metal core. Okay. And then once everything is set, this whole thing is heated very lightly so that this metal can just melt out. And so basically the idea is that you melt it hot enough to melt the metal, but not hot enough to melt the acrylic. And then you kind of just pour the metal out. And then what you get in the end is kind of flow phantom. Okay. So this is a little bit of an old school method. I think this is kind of how things were made maybe about 10 years ago. But improvements have been made, especially with the 3D printing and the casting. Okay. But this is kind of just an example of how you can make kind of a phantom like this. Okay. Another common use of flow phantoms is to test actually medical imaging technology. So things like MRIs, things like CT scans, things like that. So actually, you know, one of my good colleagues in graduate school actually worked on this, where she took a lot of these flow phantoms and she put it inside an MRI machine and she used it to test different MRI sequencing for producing images like this. Okay. So if you're going to be using flow phantoms like this, they have to be constructed a little bit differently, just because their materials have to be compatible with the machines. You know, first of all, like if you're using it to test MRI, you can't use any material that is magnetically reactive, right? So you don't want your flow phantom flying all over the room because you expose it to a magnetic field, right? And it has to be at a material that can actually be penetrated by the imaging technique itself. Okay. Okay. And so the way that you know, the way that this is done is that usually the materials that are used for the flow phantom try to mimic the physical properties of tissue and blood as much as possible. Okay. And so the reason you'd want to do this is to maybe test medical devices, right? So maybe you work for something like Edwards Lifescience and you're testing a new valve. You know, you could put it inside a flow phantom like this and put it into an MRI to see how the flow phantom behaves. In fact, I think the Edwards campus here actually does have quite a few of these type of machines that they use for testing. Okay, so let's talk about some of these material mimics, right? So you know, a big part of using flow phantoms is to get things like you know, materials that are very similar in material properties to the blood, okay, and the shells. Things like acrylic, like I mentioned, is very common for CT. Since they have very similar attenuation characteristics as real tissue. If you're going to use MRI, a lot of materials work for that as well. Okay. You have to be careful with some materials like polyester. So these don't work with MRI since they're not able to be attenuated with the MR signal at all. So they're not able to be attenuated with the magnet, and so that can lead to unrealistic images. Okay. For some of the more biological flow phantoms, the ones that the scientists actually put real cells into, you know, agar is a very popular material since it has very similar acoustic and MRI properties as tissue. Okay, and here's kind of a table down here that kind of shows some of that data. Here's some more of that data right here too. So you have agar here. I think these are all these top two here are biological. And then everything down here is more synthetic, right? So you have PVAC, so this is a plastic, urethane, C-flex, photopolymer, right? And then agar and konjac, this is a tissue. Okay. But more important than the vessel itself is the fluid that you're going to use to model the blood, right? And so ideally, you know, whatever fluid that you put into these flow phantoms, they should mimic the blood properties as much as possible. So the biggest property, or the most important property that you need to mimic is the viscosity of the blood. Okay? So the viscosity of the blood has to be around 3 to 4 millipascal seconds. Okay? So the most common way that scientists achieve this, so blood is a little bit stickier than water, so you can't just use water itself. Blood has a very similar density as water, but it's definitely stickier. So the main way, or the most common way that scientists mimic this is to make a mixture of 40% glycerol and 60% water. And so this mixture right here does a really good job of mimicking the viscosity of blood, and it has very good compatibility with MRI as well. Okay. The downside of using this mixture, so you won't see this in any textbook, but I know just from talking to people that work with this, is that glycerol is a pain in the butt to work with because it is so sticky. It's really messy. It gets everywhere. So if you spill some, you'll literally be spending days cleaning it off your lab floor. So scientists, even though they know it's important, everyone just hates working with glycerol. So it's a very messy kind of not a very nice kind of fluid to work with. So you have to be really careful. Okay. Most of the time, at least talking with people when they're first kind of testing their flow phantom, they'll do it with just water, just because water is very available and very easy to work with. And then once they've kind of calibrated everything, that's when they put in the glycerol mixture inside there. Okay. Other mimics that are just purely fluids, they don't really work with ultrasound, or they don't really work with anything, because they scatter the acoustics. Okay. And so if you're going to be testing some kind of ultrasound, technique, then you need to embed these 5-micron diameter nylon particles to help with that. Okay. So here's a little bit of more information about phantom construction. So depending on the type of imaging that you're trying to test, either MRI or ultrasound, it's going to change a bit about the materials that you're going to use. Okay. Okay. So last thing I want to talk about is just biological flow phantoms. So these are the flow phantoms that are used with real cells, right? So these are very much kind of a new thing. So very, very active area of research. But basically the idea is to create a flow phantom from some synthetic material, but then also use something that you can culture a real cell, right? So maybe you guys did this before in high school, but if you remember, you would take a petri dish and you would grow mold onto it and stuff like that. So this is kind of the same idea, and so you would use kind of the same kind of agar, same kind of materials that you put on a petri dish, but you just kind of plaster that on the inside of a flow phantom. And of course, instead of growing mold, you would grow real cells in there. Okay. So this is really cool because for a long time, if you wanted to study something like mechanotransduction, which is kind of if you remember, that's kind of the response of cells to kind of its environment. We only had kind of circumstantial evidence for this, but it's only become recently that we can actually study this kind of directly through the use of flow phantoms like this. Okay. So again, it is still very much kind of an emerging area of research, and so for the most part, most flow phantoms that do this have used very simple geometries, just because the construction gets a little bit too complicated for a realistic geometry. And so the one on the right here is actually probably the most common that you'll see is flow that actually just goes into a rectangular chamber like this. So you have flow that's pumped into this kind of rectangular chamber, and then inside this chamber is a culture here that grows the cells. Okay. So I had quite a few colleagues that had setups like this, and when I was a researcher. Okay. So even though there's a lot of variations in the setup for these kinds of flow phantoms, they all kind of have the same kind of essential components. And so the first component that they all share in common is something called endothelial plate. And so the endothelial plate are where the cells are cultured. And they're usually made of glass to kind of help with its rigidity. Okay. So usually, it takes some time for the seeded cells to actually grow and culture. And so an experiment like this that utilizes a biological flow phantom can take a while, just because it takes the cells a while to kind of grow and adhere to the plate. There's also the opposite plate. So usually they're only going to grow cells on one side of the setup. The opposite plate there is mostly just used to seal the fluid, so none of it goes out. Okay. And this is usually where the observation is taking place too. So this is usually made of some kind of optically transparent material, so you can shine a camera in there and you can kind of exactly see what's going on. Okay. The next part is the flow chamber geometry. So this is the the geometry of the actual flow chamber where you're actually flowing fluid over it. So depending on what type of geometry that you put for this, it's going to determine the flow patterns, right? So the most simple one that you can see here, this is very much just like a straight channel right here. So flow just kind of passes over just like this. And the cells are probably seated on the bottom right here. And you can see that's kind of where the microscope is. So you have just kind of a straight flow field over the cells. Okay. But there's other geometries that you can do. You can do like a curved flow. You can do kind of a sloped flow. And so, you know, you can have different geometries here that determine your flow field. Okay. You need a pump, so you need something that's going to provide energy to the flow. So the pump can either be steady or it can be pulsatile. So steady flow obviously is the most simple, but pulsatile is a bit more realistic, but also a little bit harder to set up. You need a fluid, so the fluid is there to, you know, self-explanatory, and that's what you're going to push through. Sometimes you use water, sometimes you use glycerol, depending on the setup and what you're trying to find out. And then finally, you need something to observe the cellular response. So almost always there's going to be some kind of microscope or some kind of very high-powered camera to. Okay, any questions on this? Okay, all right, so that's all I got for this. So, you know, that's all the lecture I have. So if you have questions on your project for the rest of class today, just raise your hand, I'll come by. If you're on Zoom and you want me to take over your project, just drop a message in the chat, and then, you know, you can screen share and we can talk about it that way as well. But, you know, from this point on, you know, I won't be talking anymore. You guys probably heard enough of me this semester, so it's just kind of open office hours. Yes. Yeah, let me go ahead and stop sharing. Okay.
Hi, Professor.
Hey.
So yeah, basically I do have my mesh done and
Okay.
I made the like edge size to be like 0.1
Okay.
and I get 2.9 million elements.
Okay.
So do you think I should run a test simulation on my computer or just set everything and put it on like the supercomputer gateway?
So if it's over 1 million elements, I would definitely use the cluster for that. Yeah, I wouldn't run 3 million on your computer. I mean, you can try. It just may take a week for it to finish. So I would definitely.
I got some other submissions, so I don't want to like
Yeah.
lag my computer. Yeah. All
But
right.
that's no, it looks really good. I think this is kind of, I think that's like the perfect mesh I would use for this model.
Oh, thank you.
Mhm.
Thank you, Professor. Yeah.
Over the boundary conditions, is it in the Dropbox, like that, is it that information then?
So some patients will have their pressure in the PDF, but not all of them do. If your PDF doesn't have any pressure, you can just use like a population average blood pressure. So the average blood pressure for an average human is about 93 millimeters of mercury. So I would just go with that. Yeah.
Is that the only, what other boundary condition? I know I was rewatching your video and I know you did a couple of different ones, like setting the inlet and outlets as well.
Yeah. So for the inflow boundary condition, you need the flow file for that. So you can just use the one that I posted. That one's just fine. It's just for the resistance you need that pressure. So yeah. Mhm. Actually, let me see, because I know I posted the steady flow file. I might need to post the pulsatile too. Actually, what I think I'll do probably early next week, just because I think just more people will get there. I think I'll do kind of one more tutorial on how to set up those boundary conditions, and I'll show you guys how to use the cluster too. Yeah. So I'll do that next week when more people are here.
I was like, that's all I have left. So, because like my mesh worked on the first try.
Nice.
And so then I was like, okay, I'm just gonna go with it. And then I was like, trying to do the boundary conditions, and I was like, I'm not 100% sure on what I'm supposed to be doing.
Yeah, there's more instructions for it in the project specifications and the instructions. But yeah, we'll go over it again next week.
Okay.
Especially because I think for the tutorial, I think we only did a steady simulation. So I need to show you guys how to do a pulsatile simulation too. Oh, I do have it here, actually. Okay, well, I'll show you guys how to use it next week. Oh, by the way, if you guys haven't picked up your midterms, I have it here too. You guys can pick it up.
If my estimate's like 0.07, do you think it's worth it to put it as 0.1, or do you think it's bad?
How many elements are you getting with one? That's okay. If you're going to use it on the cluster, that's fine. If you want to test it on your computer first, I would definitely try to get it down to like maybe 200,000 or 300,000.
Yeah, I just put it at 0.1 and it got down to about 1 million, so.
Okay. Yeah, anything in that range is fine.
I'm worried about running it on my computer. It's a 2-in-1, and I'm like, it could explode.
Yeah, I wouldn't run anything on your computer if it's more than 300,000 elements. Yeah. It'll run just after a very, very long time. And you basically can't do anything else on your computer when it's happening. Yep.
So the limit, should it be at, do we have a limit of the elements that we should have?
I wouldn't go past 3 million. You can, it's just gonna take a while.
Yeah.
It's gonna take a lot of memory on your computer too.
Oh, I see.
But technically, actually Tamid was showing me a measure with 10 million. So technically you can do that. It's just yeah, it's gonna take a lot of computing power. I have a bunch of computing power on the cluster. It's just, your computer may suffer trying to store all that stuff. So
So like around 2 million is like the perfect.
2 million would be really good.
Hi, Professor. Just a quick question.
Sure.
So, what will be my inlets?
So your inlet will be,
There's gonna be the inlet. There's
yeah,
gonna-
so I think that'll be cap. I'm not sure what cap that is, but if you click on the caps from the list there, it'll highlight in the on the model itself. You may want to turn off the mesh. It's a little bit hard to see things on the mesh. Yeah. Oh, yeah.
Are you gonna do the inlet notes next week too then?
So this is gonna
Yeah,
be
yeah. We'll go over that one more time together next week. Yeah. Yeah, so that's the inlet right there. If you want to do a steady simulation, we did that on the workshop last time.
Mhm.
But for pulsatile simulation, we'll go over that together next week.
Apart this, everything else is gonna be an outlet, right?
Everything else will be an outlet, correct? Yeah.
Okay, so everything else is gonna be an outlet, but I do have like 2 caps for 4, like Erudite 4A, which is like this, which is this.
Oh. Does that one have a partial intersection? One of those
It
caps
should.
might be really small. Oh, it looks smooth actually. Can you go back to your models, like all aorta? Yeah, click on, so if you click on one of the caps, like just click on one of the caps for me. Yeah, so if you go to the bottom left of the screen, do you see there it shows you the area of that cap?
Bottom left of the screen, yeah. It's
So usually when you have a non-intersecting face, the area will be very, very tiny. So if you scan over each of them, so that one obviously is very big.
This is non-intersecting, so it's very tiny.
Let's look at all the other caps and see.
This is really
Okay,
big.
that might be the one that's non-intersecting then, because everything else is, yeah, in the tens. Oh, that one's kind of small too. You can see it's highlighting in the image too, so you can see.
Mhm.
That's one that's on top. Yeah, that might be. Yeah, I think that one's fine. Yeah, it might be that one. So you might want to check the one that's really small and kind of see where that one is.
This one,
Yeah,
right?
it's probably this one, probably somewhere.
So what do you want me to do to that?
You can turn everything off except for that one. That might be the easiest way to visualize it.
Okay.
So if you click on that eyeball, it turns off the visibility.
Mhm.
I can kind of see it already. It's that kind of sliver kind of right that's kind of hanging out.
Yeah, that's very small.
Yeah, so you may have to modify your segmentation a little bit just to kind of tuck that little piece in right there.
Uh-huh.
Yeah.
Okay.
Yeah, I would fix that before you run the simulation.
Mhm. Isn't there any way to just to turn this cap off?
Well, we can't turn it off because then that would put a hole in your model. You can try to merge it with the wall. That's another thing. So if you turn your walls back on,
Aorta 1A, 4A should be.
it doesn't really matter. Yeah, just turn maybe not that one, maybe wall aorta 1.
Yeah.
Yeah, so you can try merging it with this one so you can see it's kind of part of that small thing right there. So let's see, how do we so go to so highlight both that and wall aorta 1 together at the same time. So go to face ops. Click on combine.
Combined.
Yeah.
Combined, right?
Yeah. There you go. Okay, so now that's merged into the wall. So unfortunately now the model has changed, so you have to remesh it again.
Yeah.
But then that should you know that should prevent. Oh, you may have to change. I think it merged it all into the cap aorta 4. So you may have to change the name of that to call it a wall. So
This?
yeah. So change the type to a wall. Or you can change the name too. Like you can change it, you can change to like wall aorta. Yeah. And then on the column next to it, you see it's labeled as a cap. Go ahead and change that to a wall. Yeah, there you go. Okay. So go ahead and go ahead and save the project and then remesh and then yeah, you can go from there.
Oh, thanks for that. Yeah, I changed the solver.
Yeah.
The 2019 one and it worked.
Yeah.
And I ran the simulation on my computer with the mesh did like not like an accurate mesh.
Yeah.
Enough.
Uh-huh.
It was like 200,000 cells. But it took like hours.
Yeah. It's
like I went to the gym, I came back and it was at 20%.
Yeah.
I was like, what?
That's why people were asking like, can I run it with the 1 million? Like you could try, but it may take like a week for it to finish.
Yeah.
So that's normal. That's
Okay.
pretty normal. That's why we're gonna use the clusters. Actually
cluster.
on Tuesday next week, I think when more people come, I think I'll do another workshop where I kind of go over the simulation stuff again.
Okay.
And I'll show you guys how to use the cluster and how to visualize the results too. So
Okay.
yeah, we'll do that on Tuesday.
Okay.
Yeah.
Sounds good.
Mhm.
And that's when we're gonna learn peer review too.
Yeah. Yeah. So peer review is what we use to visualize the results. Yeah. What does the error say, Caleb? It just says there's an error in creating the files or failure to create the files or whatever.
Let me see. It says in specific failed to finish creating data files.
Yeah,
but I
I-
double checked.
So I
and
so I
have
think
the-
some instances and when you click on show details, it says nothing in there, right? It's just blank.
Sorry, could you say that again? My internet kind of cut out.
Oh yeah, so when it says it failed to create the files and you click on show details, it's just blank in there, right?
Mm-hmm.
Okay. So there's an error with certain instances of Windows. It's very hard to recreate, but basically what you need to do is you need to install an older version of the solver to get it to work. So I'll send I think I'll send an email to everyone later today with those instructions. Yeah, it's a little bit of a complicated fix.
Okay, glad it's not my mesh
Actually,
or anything.
let me forward you the email because Marvin was having the same issue. So let me forward you the
Okay.
email right now just so you can get it started.
Okay. And you said that for an aorta model, the total number of elements should be right under 2 million would be good for the simulation, right?
That's pretty good. Yeah.
Okay. That's what I got it to.
All right, Caleb, I just forwarded an email to you. So that email has the instructions on how to install an older version of the solver. It should work on that one. But yeah, I'm gonna send those out to the class later today, but I just need to format it for Canvas.
Okay, cool. Thank you very much.
Yep.
I'll email you if I have any other questions.
Okay. So for this one, this model right here is an aorta femoral model. So my was that my voice? Someone playing it.
Those dad related.
Yeah, yeah. When someone's playing a recording.
We're just asking.
Yep. Mhm.
But I haven't ran my like mesh yet, because like last time, when I asked you, I should probably fix up like my model.
Yep. Mhm.
So I was kind of wondering, like where, like should I, like what part of it should I fix?
I think it was more that the model. I think I remember correctly. I think this part of the model looked fine right here. It's just some of these branching vessels were, not really matching where they was. So this geometry is tough just because there's so many vessels that are kind of crisscrossing around that area. So it kind of looked like to me like we were kind of maybe grabbing some of those the wrong ones. At this point, I think it's okay though. I think let's just go ahead and mesh it.
Okay.
Yeah. So I would go ahead and just try mesh and just go with it for because you got the main one here. I think that's the main one because this right here, this is the your vena cava. So that's the main vein. And these are connected directly to the pulmonaries, which go out kind of like this way. So you have one that goes out this way, the other one goes out that way. So you have one side is pretty well developed, but the other side is. But you have the main, which is for sure.
So I got like this main one and then these two. Yeah, and the rest are kind of like a little like weird.
Yeah. Okay. But I think it's okay. I think for now, I think let's just work with this. The meshing is always the hardest. Once you get past the meshing, it's so you need a size first. So click on estimate for the size. It looks small, but then these models are also much smaller too. So it might be okay. Same thing as once you get run measure, it's a commitment. Go ahead and hit. Let's try it. So go ahead and run the measure. Yes. It's going to think for a while. If you want to monitor how it's going, like Symvastra also opens up the command. So let's go ahead and open this window here. Okay, eventually it's going to reach a point where it's going to say iteration 1 out of 10, 2 out of 10. If it reaches that point, then you're probably in pretty good shape. Okay. It just takes a while. Usually if it takes more than like 10 minutes to make the mesh, then There we go.
Okay.
Okay. Should be okay, or should be okay.
Mhm.
It may take 5 minutes or so to make the mesh, but. You can see, so after the mesh completes, a window will pop up to tell you how many elements are in the mesh.
Okay.
If it's like. You know, like if it's over 3 million elements, I would try to make this a bit bigger. So there's kind of an inverse relationship between the edge size and. So, yeah, I would make that a bit bigger. It looks like your mesh might be a model, just for this kind of thinking.
Okay.
But yeah, give it a try and just tinker around with that number. Try to get the mesh under like 2 million would be like.
2 million, okay, and then what exactly is like the edge size? Is that just like from like edge to edge? How-
That's how big the element itself is. So the elements are they're all kind of triangles. And so the edge size is how big the length of the triangle is.
Okay, so, okay, for sure. Thank you.
Yep.
I think it's gonna work. I'll just like run it. And you 20. No, I could like leave it.
Oh,
Like charging and. like, Fifteen. You present.
Yep.
Hey, Professor, where do I find the mean pressure and the flow in retreat?
It might be in your PDF. So
Okay.
I would check there for if it's not in there, not every patient has data. You can just
No, I
use
don't have it.
population average pressure.
Okay,
So the population average blood pressure for most people is around 93 millimeters mercury.
okay,
And the flow rate that we're using is about 100 milliliters per second.
okay. Thank you.
Yep.
Oh, excuse me, Professor.
Yep.
I had a quick question. Earlier we were talking about how like the blob was okay, and I should just make the other vessels stick out of the blob instead of going all the way to the main aorta.
Yep.
Um, wait, let me. Is it cool if I share my screen?
Sure.
So I'm trying to make it so that the let's see, vessel one. Oh, here it is. Yeah, it's coming that it comes out of the blob part,
Okay. Yep.
right? So I took off the segmentation. Let's see. Sorry about that. Let's see. Take off that. So there used to be like a larger segmentation right here.
Yeah.
I took that off. When would I just leave the path here too, or would I
Yeah,
what-
leaving the
crazy.
path there is fine. So when you make the
Okay.
model, it only counts the segmentation. So yeah, that's perfect actually. So just I would just delete the segmentations up there and then yeah, that looks really good. That looks much better.
Okay, and then so I just because I think I right now let's see, I think I deleted the oh no, I didn't delete it, it's still there. Okay, then so just don't delete the path, just segmentation, right?
Exactly.
Just
Yeah.
okay.
Yeah, maybe just delete the first 2 or 3 segmentations that start in the aorta and then just have the first segmentation come off that branch there.
Okay, I see. Okay. So then I would just let's see. Just make the model again, right? Just make do it again.
Yeah.
Yeah.
We're gonna
And
make
then
the model then.
create the model that. Okay, I see. There you go. So now it's just coming out of the
Perfect.
yeah, it's not because I do remember showing earlier that it was sticking out, making the blob even larger.
Yeah.
So now it's like coming out of the blob
Perfect.
itself.
Yeah, looks great. Looks really good.
Okay, and this part right here, would you like me to smooth this out a little better? Because it does kind of based on
We
the
you can smooth that in post. And so if you
oh
remember,
right.
yeah, so I would put everything in one model first, and then you can
Okay.
kind of smooth some of those intersections a little bit. That's fine to do in post, but yeah, you want to make sure that those vessels come off well.
Okay, for sure. Yeah, okay. Thank you.
Yep. Yep.